Hello everyone. In this section we're going to be looking at items known as absolute value functions and then a topic that's related to them called piecewise functions. To start, the piece of prior knowledge that you need in order to set yourself up for success today is how quadratics transformed in vertex form. So could you describe where the vertex was transformed to as a mathematical phrase based on the given vertex form equation? So either at the top of your note packet or on a loose leaf of paper, I would like you to try these two warm-up questions. These are the pieces of information you need to be able to recall in order to do the first part of today and then set yourself up for the second part. So if you would, try these two questions, pause the video, give yourself a chance to try it authentically. After you've given maybe a minute, come back and we will see how it went. So pause the video now, please. So here we go. We practiced these a lot recently when we were studying quadratics. This first one, the vertex is shifted. This will move it right 4 and up 8. So you would say vertex has been shifted right 4, up 8. And if you're going by order of operations, you would go right 4, then technically this would occur next. And the negative out front is going to open it upside down. So it would go right 4, then flip upside down, and then move up 8. And if I ask the program to graph it, I'll see that is exactly what occurred. So there's the first one. The second one, this plus 5 is past a negative 5, so that's going to move it actually left 5. Another way you could see it is what would x have to be in order for this thing to be 0? It would have to be a negative 5, so that's why it's got to go left 5. This one would have to be a positive 4 for x in order for it to be on the x-axis, so it would be a positive 4, right 4. So we go left 5, then this 3 is going to make it steeper. It doesn't flip it upside down because it's still positive, still opening up. And then this minus 6 is going to move the graph down 6. And again, I'll ask the program to graph it. Oh, it's not wanting to do that one. Oh, here, we'll sketch it right now. It would look like this. So I'd go left 5, and then down 6. So the vertex would be right there. And then it's going to open up and have a steepness of 3. So I would go up 3 units and then right 1. So the graph for this would look something like that. There we go. That's what you need to recall. We're going to be doing that with a new function today, and that new function is called an absolute value function. So if you would, have your note packet out. It should start with this. So the first thing that we're going to do, if we don't know what this function looks like, is we do what we've always done. We just make a table and plot points and see what pattern develops. So the new function is, it's called the absolute value function because every value for x that I give, the output, the y values, are going to be whatever the absolute value of that is. So f of x is equal to whatever the absolute value of x is. It's the exact same thing as if I wrote it as y equals the absolute value of x. I'm just calling this specific rule f because it's a function. When we're picking x values, you can pick whichever ones you like, but technically we tend to choose between -2 to +2 because it gives a nice snapshot around the origin. So if I plug in -2, well, the absolute value of -2 is +2, so I get 2. So this would be the point -2, 2. If I put -1 in there, its absolute value is 1, so I get -1, 1. If I put 0 in there, I get 0. So far it's starting to look like a line, but this is where it's going to change, because if I put 1 in there, I get 1 again. If I put 2 in there, I get 2. If I put 3 in there, I get 3. And so you can see it's going to make this V pattern. That is our parent function for absolute value functions. You might notice that it looks like y equals x. I'll sketch that here in red. The difference is where y equals x goes negative, though, my absolute value function is going to make it go positive. So this left side is the same. This right side is then a reflection across the x-axis because it's taking the positives. Yeah. So that's our parent function for absolute values. Now what we're going to do is we're just going to start to transform it. The first thing I should mention is the second part of this lesson is on something called piecewise functions. And technically, this absolute value function, let's get rid of that red one. This absolute value function here, shown in black, is a piecewise function. The reason it's piecewise is it comes in two parts, as you can see, the left part, and then it's got this kink, and then it forms the right part. So technically, to write its equation, I would need to write two different equations because it's kind of got two different parts. So there's another way I could write this. I could write it as the absolute value of x, or I technically could write it in the following way. So we would write f of x equals, and then we use these curly brackets because we're going to have a list. Depending on the function you're writing, it might have more than like two parts. This one will have two. And we're going to write the two parts that make up this equation. So I'm going to kind of color code this for ourselves. So there's this left side I'm going to do in blue, and then there's this right side, which I'm going to write in green. If I were going to write the blue part, well, this blue part follows the line negative, y equals negative x. So I'd say it's negative x, and then we put a comma, and then we write when that is applicable. When does it follow this line right here? When does it follow that equation? When does it follow y equals negative x? Well, it follows y equals negative x so long as x is less than or equal to 0. We'll say that the blue part gets the origin because the origin can't be blue and green. We got to pick one. So we'll do it for the left side. Technically doesn't matter. Now I need to write the green equation. The green equation follows a different one because it has a positive slope. So it would be the line y equals x, which we just would write as f of x equals x. And then we put a comma, and we need to write when this is applicable. Since the blue one got 0, we would say this applies when x is greater than 0. And so it's another way of writing the absolute value equation or absolute value function. And we need to write it as two different parts because technically it has two different parts. And that's called a piecewise function. A piecewise function is a function that requires two or more expressions to define it. Now what we're going to do is we're going to do exactly what we did with quadratics. We're going to transform the absolute value function. So we're going to take our parent function, this right here, and we're going to transform it. So what types of things can we do? Well, what did we do with quadratics? We moved it left, right, up, down, and then flipped it upside down or made it steeper and wider. And the same thing's going to go along here. So I'm going to make a table, and then I'll show you how you can do it actually much quicker than making a table, but we'll do the table to start. Technically, we usually go from -2 to +2, but this one, I'm going to notice this is going to shift it right 1. I'm going to pick x is 1 because if I put 1 in there, it'll make this part be 0, and that will actually tell me where that vertex is going to be, that change point, the kink point I referred to earlier. So my center is actually going to be at 1 because it'll make the part in parentheses, the absolute value, equal to 0. So I'm going to center this at 1, and I'm going to pick some values around either side of it. So if I put 1 in the equation, maybe to start, 1 minus 1 is 0. 0 plus 2 is 2. So 1, 2 is going to be where my vertex actually is, the center of my graph. Then I can put 2 in there. 2 minus 1 is 1. And 1 plus 2 is 3. If I put 3 in there, 3 minus 1 is 2. 2 plus 2 is 4. Then I could put 0 in there. 0 minus 1 is -1. And the absolute value of -1 is +1. And 1 plus 2 makes 3. So I see there's this symmetry going on again. The same thing that happened with parabolas. If I put -1 in there, I'm going to end up getting 4. So I've got the following points, and I can sketch in the equation and the graph of the equation, and it looks like that. If I look, what happened to it? Well, it has the same steepness, right? It's still up 1, right 1, up 1, right 1 on the left, and down 1, right 1, down 1, right 1 on the left. Or on the, sorry, it's up 1, right 1 on the right, down 1, left 1 on the left. The reason why is because the number out front is still a 1. The steepness is still a 1. The only thing that happened is the vertex got changed. It got shifted right 1 and up 2, and that's what happened to this guy. It got shifted right 1 and up 2. So quicker way I can just plot these is plot the vertex and then use the steepness to do the right side, and then just do the reflection to do the left side. It's actually the exact same strategy we used for parabolas. If I go looking here, like when the program wouldn't graph this one, what did I do? I shifted the vertex left 5, then down 6, and then I used the steepness of 3 over 1. So I went up 3, right 1, sketch the right side, and then I just reflected to get the left side. It's the exact same thing. We just have a different parent function. We're graphing absolute values, which would make v's, as opposed to quadratics that made parabolas. I'm going to try one more, then I believe I'm going to have you try a couple. So here we go. This one I know is going to shift at left 3. What value for x would make this thing be 0? Because that's where my vertex is going to be located in its x coordinate. It would be a -3. So -3 is going to be the center of my table. It's going to be where my vertex occurs. If I put -3 in the equation, -3 plus 3 is 0. 0 times 2 is 0. So I know my vertex is actually going to be right there. Then I pick some points on either side, -2 and to -1, -4, -5. A couple on each side will be good. If I put -2 in the equation, -2 plus 3 is 1, 1 times 2 is 2. If I put -1 in the equation, -1 plus 3 is 2, 2 times 2 is 4. And then I know this is just going to make the mirror image. This is a 2 and this is a 4. You can check by plugging the points in yourself. I plot. I get this side, and then I could just reflect to get the left side, but I have the points as well, so I sketch it in. The graph would look like that, and I'd be done. So you can always make a table and sketch it. The easier way for this one would be, no, it's going to shift left 3 and then up 0. Technically, there's a +0 going on here. And then I know the steepness is a 2, so I go up 2, right 1, and I can continue to go up 2, right 1 because absolute values are lines on each side. So I could get all of the right side, and then I just reflect, and I know that this side is going to be a slope of -2, down 2, left 1, down 2, left 1, because it's just the reflection of the right side across the axis of symmetry. So there we go. Going to give you a chance to try. So if you would, please pull out your whiteboard and try the following two equations and to graph them on the same graph. It'll be fine. So pause the video now, maybe for a minute, minute and a half. Check with a neighbor once you've done both and see how they compare. So pause the video now, come back after you'd like to see what the answers are. Okay, so welcome back. I'm going to do these without making a table because I know how transformations work. So there's a 1 out front. That's going to be my steepness. The vertex is going to go right 1, up 3. So there's the vertex. I know the steepness is 1, so I go up 1, right 1, up 1, right 1, up 1, right 1. There's the right side. If I reflect on the left side, it's going to be a -1 for the slope, and there'd my graph be. Second one, I know this is going to go left 1 and up or down 0. There's no such thing as a negative, but you could think about it like that. So left 1 and then up 0 will be right there. This one has a steepness of -2, so it's going to be opening downward. So the right side would be down 2, right 1, down 2, right 1. So there's this side. And then I just reflect on the other side, going down 2, left 1, down 2, left 1, and there'd be the left side. So there we go. That's how long they take. They go pretty quick. So that's absolute value functions. Absolute value functions are a specific type of piecewise function. The second part of the lesson is we're going to graph other types of piecewise functions. So here's a different equation for a new piecewise function. You can see it has two different equations because this graph has two different parts. It tells me when I would do both. So to do this, what I'm going to do is I'm going to sketch both of these at first. I'm going to use some colors to denote it, and then I need to go back and I need to erase. So when you're doing this, you might want to just sketch these in lightly, draw your lines lightly, because you're going to need to go back and erase some parts, because it says that this graph is only, each equation is only applicable, only appropriate in certain circumstances. So these right here tell you what the graph is going to be, and these conditions over here tell you when that graph will be occurring. So let's do the blue one first. I'm going to sketch in -2x minus 3. That's a line. Y equals mx plus b. I'd start at -3 and the slope is -2. So down 2, right 1, down 2, right 1. If I can't do that, I can go up 2, left 1, up 2, left 1, up 2, left 1, up 2, left 1. And if I were drawing it in, it'd look like that. So there's the blue part. I'm going to need to go back and erase just a little bit of this because it's only applicable when x is less than or equal to 1. Now I'm going to do this red part. So this is the equation y equals 4. That's a horizontal line, so that'd be right here. So there's the two equations I'm graphing. However, both of these are only appropriate in certain circumstances. So let's do the blue one first. It says the blue one is only valid when x is less than or equal to 1. So it's only, here's my x-axis, so it's only valid, let me use some shading. It's only valid when x is less than or equal to 1, so only the left side. Once it goes to the right, it is no longer valid. So I need to erase part of this blue line, and that blue line will no longer be valid for anything to the right, a positive one. It is only valid when x is, it says, less than or equal to 1. So only from here going to the left. So the only part of the blue one that's valid is this. It does not go to the right. The red one picks it up from the right. It says the red one is only valid when x is greater than 1. So if I were looking here, the red one is only valid on this part. So I need to erase the left side of that red line because it is not valid when x is less than 1. So I go back and I'm going to erase this red line for when x is less than 1. And it doesn't say equal to, so I actually need to do an open circle there. We're going to talk about why. The reason why is because if I asked you what is the x value, sorry, what is the y value when x is 1? Well, what x is 1 right here, it needs to know, is it going to go up there or is it going to go down here? And if both of those were filled in, this wouldn't be a function. It would fail what's called the vertical line test that we studied earlier because both of these would be filled in. But now because this one's open and this one's filled in, we know that when f is 1, it needs to go down to the blue one, which is going to be at -5. So that's why one of those at the transition has to be open and one has to be closed. But there's the graph. I could find any x value. So if I gave you an x value like x is 6, I know I'm going to be on the red. If I gave you a value less than 1, like -3, I would know that you're going to be on the blue part of the equation. So the domain is all of the x values that occur on this graph. The graph goes all the way to the left and all the way to the right. So this domain is all real numbers for x. The range, though, if you look at what y values you get, well, really this red line doesn't help us with y values because it's always 4. But this blue one says you'll get all y values and keeps going up and up and up. You'll get all the positives, and then you go down and down and down, and the smallest you'll ever get is -5. So your range this is going to be any y value that's greater than or equal to -5. The domain are what x values you get. You get all the values going left and right. The graph, though, goes only so far down. It's limited by this blue part of it. So that would be the domain and range for this. We're going to work one going backward, then I'll have you just try graphing one piecewise. So working the backward is, what if I gave you the graph and asked you to write the equation for this? So here we go. Let's do it. We usually read it left to right, and we usually write the first one on the top. So let's do this one right here. This one's in blue. I need to write this equation. Well, I can see right here the y-intercept of this graph is -3, and the slope is down 1, right 2. So -1/2 x minus 3 is the equation. Then I put a comma, and I write when is this part of the graph valid. It is valid so long as your x value, we always write it in with respect to x values because those are your inputs. We are on this part of the graph so long as x is less than or equal to 2. Now I need to do the top one. This one right here, I need to write this using point slope. You could work backward if you'd like to figure out the y-intercept. I'm just going to use point slope. I can see the point is 2, 1. So my y value is 1. My slope I can see is going up 1, 2, 3, and over 2. So I go up 3 over 2 for every x past 2. That's my old Bruin point slope form. And when do I do this red one? I do it so long as x is greater than 2. So you could write it in Bruin point slope. If you wanted to, you could work backwards and figure out that it's going to cross at -2. You could have written this red part as 3/2 x minus 2, and that would have been fine as well. Either one. I just did it in point slope. Now I need to state the domain and range. The domain, I can see this blue part of the graph is going all the way to the left. This red part of the graph, you should erase that, that's not actually part of it, is going all the way to the right, and we get every x value in between. So the domain is all real numbers for x. All real numbers for x. The range, I go all the way up because the red one's going all the way up, and so is the blue one, just a little slower. They don't go all the way down, though. The smallest we get for y is -4, so we get all y values that are greater than or equal to -4. That would be the range. The range is the spread of my y values. It's kind of the range of the y values, and the domain is the spread of the x's, the range of the x's, if you will. Just two different types of range going on there. Okay, I'm going to have you try. If you would, please pull out your whiteboard and sketch the following piecewise function. So it's going to have two different parts to it, and each one is valid in different circumstances. So pause the video now for maybe a minute and a half, 2 minutes. Unpause it once everyone's had a chance to try. Okay, here we go. I'm going to go a little fast over this one. So I'll do this top one in red. Its y-intercept is 0, and then I go up 1, right 2, up 1, right 2, down 1, down. So technically, its whole graph would look like this, but this graph is only valid for x values less than 0, so I actually don't want the right part of this graph. So I'm not going to graph that part, and this one's an open circle because it doesn't say equal to. So it looks like that. Then I'll do the second part in purple. This one starts at 3. Its slope goes up 2, right 1, up 2, right 1. And I would sketch this going back down to this way, but this says this is only valid when x is greater than or equal to 0, and that's right here. So this one actually is only going to be sketched on the right side. So that's what the graph would look like. The domain, this red part's going all the way left, the purple part's going all the way right, so my x values are all real numbers. Another way you could write that is you could say that x goes in between, x goes in between negative infinity to positive infinity. It's another way of writing all real numbers. The range, this is going all the way down, and this is going all the way up. However, you don't get any values in between 0 and 3. You do get 3, though. So we would say that my range is going to be, we kind of have to write this in two statements. We need to state that the y values go from negative infinity all the way up to 0, but we don't get it. That's kind of the red part. And then we get this purple part, which is going to be I get any value from 3, including 3, heading towards positive infinity, but I don't get anything in between. So that's one way of writing it. I could write two different statements. Or I could say I get all y values except for those between 0 and 3, not including 0, but including 3. That's a lot to write in English, so we have these notations. So there we go. Another way you might see this written, this is kind of for a future class, is you could say, you could use what's called bracket notation. So we could say that this goes from negative infinity. We use parentheses if you can't get there, and I can't get to negative infinity, and I can't get to 0 either because that's open. So I could say that, and because I can get to 3, because it's equal to, we use a hard bracket as opposed to the parenthesis, comma, and then all the way up to infinity with a parenthesis because I can't reach that. So I could use brackets if you don't like the less than notation. So there we go. That is it for today. Thank you very much. And oh wait, is there one more? Oh, sorry, there's one more. There's an application one I wanted to talk about. So sorry, one more item I wanted to show you is just an application of where Piecewise gets used. They get used a lot of times when being charged for things, where they charge you a rate for a certain amount, and then you get charged extra if you go over that. So cell phones are a good example. So let's say a cell phone company charges you $50 for your first 5 gigabytes of data. After that, it charges a rate of $10 per gigabyte for every gigabyte you use over 5, right? What the following piecewise function would be. So the situation is, this is a cost function. So you could call it C if you want to, but we're just using f of x. So the cost is equal to $50 flat rate, and you get charged $50 so long as your data usage is less than or equal to 5. After that, what happens? Well, you get charged $50 plus an additional $10 for every gigabyte past the 5th one. So you got to use your point slope form for that. And that is valid if you use over 5 gigabytes. So now we could use it to calculate what would the cost be if I put 6.5 in for x. Well, do I put it in the top or the bottom? I look, because my x is bigger than 5, I'm going to be using the bottom equation. So I will put it into there. 50 plus 10 times 6.5 minus 5. That's going to be 50 plus 10 times 1.5. So I'm going to be charged an additional $15. And my total then would be $65. So that's just an example of where Piecewise gets used. They get used for when you're charged different rates depending on what you've used. That is the end of the discussion. Thank you very much and have a good day.